Another discovery which led up to quantum mechanics was line spectra of elements. Each element has its own characteristic spectrum of wavelengths emitted when energy is applied to that atom. Rather than being a continuous band of energy spanning all wavelengths, only certain wavelengths get emitted from each element. These line spectra are useful in identifying elements in faraway stars and planets because they are unique for each element. Line spectra can be explained with a model of the atom put forward by Niels Bohr. He said that electrons can be found in orbits around the nucleus, just like planets orbiting the sun. Each has a certain distance from the center as it travels its path. I am going to use the term energy levels because it is more correct. The energy levels that are closer to the nucleus, like n equals 1, are lower in energy. The energy levels that are farther from the nucleus, like n equals 3, are higher in energy. As electrons absorb or take on energy, they move from a lower energy level to a higher energy level. For example, an electron can go from n equals 1 to n equals 3, or n equals 2 to n equals 5. As electrons emit or give off energy, they move from a higher energy level to a lower energy level. For example, an electron can go from n equals 3 to n equals 2, or n equals 4 to n equals 1. The energy that is emitted is in the form of light, which corresponds to lines in the atomic line spectra. Each of these electronic transitions has a particular energy associated with it, and therefore a particular wavelength. Remember, if you know energy, you can solve for wavelength using the two equations we've talked about so far in this chapter. If we know the numbers of the starting and ending energy level, we can calculate the wavelength of light that will be produced using the Rydberg formula. This formula is 1 over wavelength equals the Rydberg constant, R infinity, times 1 over nf squared minus 1 over ni squared. Notice that this equation is solving for 1 over wavelength rather than wavelength. For the process of emission, the starting energy level, Ni, is always higher than the ending energy level, Nf. Since the equation is solving for 1 over wavelength, the units of the Rydberg constant are meters to the minus 1, or in other words, meters in the denominator. Using this equation, we can figure out which electronic transitions correspond to which bands in the line spectrum. In this example, we are calculating the wavelength of light in nanometers of a photon emitted when an electron moves from the n equals 3 energy level to the n equals 2 energy level. We start with the Rydberg equation and plug in our values for our energy levels. The initial energy level is 3, so that gets plugged in for Ni. And the final energy level is 2, so that gets plugged in for Nf. Don't forget the squares in the equation, so we do 2 squared and get 4, then 3 squared and get 9. So our fractions are 1/4 and 1/9. We want to combine our fractions, so we need them to have a common denominator. We can express both fractions with a denominator of 36. 1/4 is 9/36, and 1/9 is 4/36. 9/36 minus 4/36 is 5/36. We plug in the value of the Rydberg constant, which is given in the problem. You do not need to memorize it. We multiply the Rydberg constant by our fraction of 5/36 to come out with 1.524 times 10 to the 6 meters to the minus 1. Notice this is not our answer yet. It only gives us 1 over the wavelength. To get the wavelength, we take the inverse of that number. In other words, we do 1 divided by our value of 1.524 times 10 to the 6 meters to the minus 1. That gives us 6.562 times 10 to the minus 7 meters as our wavelength. Since the question asked for the wavelength in nanometers, we divide by 10 to the minus 9 and come out with 656.2 nanometers. This value corresponds to the red region of the spectrum and is therefore a red line. What is the wavelength of light emitted when an electron in a hydrogen atom goes from n equals 4 to n equals 1? The Rydberg constant is 1.097 times 10 to the 7 meters to the minus 1. Is the answer A, 0.0103 nanometers, B, 122 nanometers, C, 97 nanometers, or D, 1.07 nanometers? The correct answer is C, 97 nanometers. We plug in 4 for the initial energy level and 1 for the final energy level. We square each of those numbers to get our fractions, then combine the fractions by giving them a common denominator before subtracting. We come out with 15/16 for our fraction. We multiply the fraction by the Rydberg constant and come out with 10,284,375 meters to the minus 1 as 1 over wavelength. We take 1 over that number and get 9.7 times 10 to the minus 8 meters as our wavelength. Since all the answer choices are in nanometers, we convert to nanometers by dividing by 10 to the minus 9 and come out with 97 nanometers.